For today's video, we'll be talking about oxymercuration-Demercuration for alkenes. So we have an example. This structure was reacting with mercury, Hg, also with acetate for short, this is acetate for short, two acetates, and with water. But also the second step for this would be NaBH4. And so when we draw its product for this, we'd redraw the molecule. This is a Markovnikov problem, and so we would put the H on the least substituted carbon, while OH would be on the most carbon that has the most substituents. Next, if we have a structure like this, and this is reacting with the same thing, we have mercury, and then also we have acetate, and this is with water. All over, the second step would be NaBH4. Now to draw its product for this, we redraw the molecule. Oops. And so the double bond is at, it was between here, it was between here and here, and so the hydrogen would be on the least amount of substituents. The carbon that has the least amount of substituents, which would be there, and now the OH would be on the carbon that has the most substituents. Will be there. Actually, it will be there. Okay. So now let's talk about its mechanism. For the reagents, we have mercury, and then we have water. We also have the NaBH4. So this is the oxymercuration-Demercuration reaction. First thing you want to do is redraw the alkene with the pi bond, right? And now we draw the mercury from a reagent. It's connected to 2-acetate. It is 2-acetate. This is because we have the 2 subscript over here. And so for this, both of these oxygen has 2 lone pairs. Mercury has 1 lone pair. The pi bond is the nucleophile, the Lewis base, attacks the mercury. Right when it does this, it doesn't attack the mercury, actually it grabs the mercury, right? Now, the sigma bond goes to the oxygen, the electrons, right? And so for this, we would have a step, which we would get this. Now, this carbon is connected to this mercury. Okay, the other mercury got kicked off, so it's by itself. On the other side, added with, has 3 lone pairs with a negative charge. This mercury still has 1 lone pair. Now we add the carbocation. This is because the carbon lost, the double bond has been lost. And so we would add a positive charge on that carbon that has the most amount of substituents. So mercury goes on the carbon that has the least amount of substituents, or the carbocation goes on the carbon that has the most amount of substituents. This is because to make it more stable. Now from this we have mercury, this lone pair, going to attack that carbon. This would give us a result of forming a cyclic membrane, right? So both of these carbons are connected to the mercury, right? Mercury is still connected to that acetate, and it has a positive charge. We still have that acetate on the other side, it's added, with a negative charge. Now from here, we add our second reagent. From our first step is H2O. So water comes in, it attacks the carbon that has the most amount of substituents, so it's either this carbon or it is that carbon. This is because it's connected to that mercury, both of them, and also that there was the double bond on those 2 carbons. So from this, the lone pair attacks the carbon that has the most amount of substituents, would be that. That carbon gives off its sigma bond, its electrons, to that mercury, and we will get a result of redrawn the molecule. Now its mercury is only connected to 1 carbon, has its lone pair pack still connected to that acetate. Now we have oxygen with 1 lone pair connected to 2 hydrogens. This gives off a positive charge. From the step, we still have that other acetate from our problem, has 3 lone pairs with a negative charge. From here, one of the lone pairs from acetate with a negative charge wants to deprotonate that oxygen. So we would go to that hydrogen. It grabs this hydrogen. This hydrogen gives off its electrons to that oxygen. Forming mercury still here with that acetate. And now we have something called the OH actually. OH comes in that has 2 lone pairs. We still have the other acetate which is connected to a hydrogen. So acetate connected to the hydrogen. So now we are done with the oxymercuration step. We have oxymercuration means adding the OH and the mercury on the structure, which we have done. Now for the demercuration step, meaning removal of mercury, we would react this with our other reagent on the second step, which is NaBH4. So react this with NHBH4. For this, the mechanism is very complex. So all we do is redraw the molecule. Okay. Keep the OH, right? All we do for this is that we take this mercury and change it to a hydrogen. Okay, and for this, we just drop this for now. Okay, erase that. So now the hydrogen is on the carbon that has the least amount of substituents. OH is on the carbon that has the most amount of substituents. This makes sense, and this is our final product for this mechanism. Next, if we have this structure, this alkene, that is reacting with mercury, water, and also NaBH4. This is the oxymercuration step, so all we do now is redraw the alkene and also redraw the mercury connected with 2 acetate. And this has 1 lone pair. So from this pi bond is the nucleophile. It would go to the mercury, grab that mercury. The mercury gives off that electrons to that oxygen. So we would get a result of this. Mercury would go on the carbon that has the least amount of substituents, still connected to that acetate, while the other acetate is by itself with 3 lone pairs. It's a negative charge. And also we add the carbocation that goes on the carbon that has the most amount of substituents. This is because to become more stable. Mercury still has 1 lone pair. It attacks that carbon that has the positive charge. From this, we would get a reaction of forming a cyclic membrane, meaning that these 2 carbons connect to each other to the same element. This would be mercury in this case. So mercury is still connected with that acetate, but also the other acetate is still on the product, still on the side, with 3 lone pairs with a negative charge. Mercury has a positive charge in this case, selecting electron density. So for this, we add our other reagent, which would be water. In this case, water comes in, attacks the carbon that has the most amount of substituents. So one of its lone pairs would go and attack that carbon. Well, that carbon gives off its electrons to mercury, right? So for this, we would get a reaction of this. Now the O comes in, the oxygen, has 1 lone pair connected to 2 hydrogens, and still we have that mercury still on here. So the acetate plus the other acetate that is in the problem with 3 lone pairs with a negative charge. From this, one of the lone pairs of the acetate with a negative charge, before this OH has a positive charge. The oxygen connected to 2 hydrogens. So from this, the lone pairs from the acetate would go on that hydrogen, right? Grab that hydrogen, and that hydrogen gives off electrons to that oxygen, like that. So this would give us a result of redrawing the molecule and having OH. Now it's connected to this acetate still. Now we have this H connected with the azo acetate. From this step, we would have to do the demercuration step. This is because we have completed the oxymercuration step, which is adding the OH and the mercury on the structure. So from this, we would use our other reagent from the second step and react this with NaBH4, and all we do is just remove that mercury that is connected here and put a hydrogen in and also drop that. And so from this, we would redraw the structure. One product, we still have the OH, and we also have the hydrogen now instead of the mercury. This makes sense because the hydrogen is on the least amount of the carbon that has the least amount of substituents. OH is on the carbon that has the most amount of substituents. And so this is our product for this mechanism that we drew.